All right, so welcome to my series of videos on statistics. Please, I would like you to like, comment, share, and let us have your feedback. Now, in this video, I'm going to introduce you to describing data using numerical measures. One of the things I want you to know in statistics is that when we want to describe data, we can describe data using graphical measures. And then we can describe data using numerical measures. All right, we can describe data using numerical measures. So that is the focus of this lesson. Now, by the end of this lesson, we should be able to understand the various ways of describing data in terms of measure of central tendency, or what is basically known as the average. So by the end of this lesson, we should be able to understand the various averages that we have. Then we should be able to understand issues of dispersion, because once we have an average for a set of figures, we need to know how far the individual figures are from their average. Okay, so we are going to learn a couple of measures of dispersion, and that will lead us to doing a box and a whisker graph and interpret it. We will also look at computing measures of dispersion like the range, the interquartile range, the variance, the standard deviation, etc. Then afterwards, we are going to learn how to standardize values. And then finally, we are going to learn how to compute the z-score, the coefficient of variation, understand how they are applied. Then to cap it all, we are going to understand the empirical rule and then the Chebyshev's theorem. Now, when we look at descriptive statistics is about two things. Because if you want to just describe data, we can describe data using two measures. Number one, we want to know the summary measures. We want to know the summary measures. So for instance, if I collect data on the scores obtained by students in a statistics text, and I want to describe that data, one of the simplest ways I can describe that data is to summarize the scores. Okay, so descriptive statistics basically is about summary measures. Descriptive statistics basically is about summary measures, or what is known as the averages. Now, I want you to understand that the summary measures or the averages or the measure of center or the measure of location, these are synonymous phrases. So the measure of average is the same as the measure of the center of a data, is the same as the measure of location of the data, and is the same as an average. Now, I want us to go beyond this meaning of average. When we say the average of something, what usually comes to mind is the mean. But at this level, I want us to go beyond that to note that the averages include the mean. Mean is an average. Median is an average. Mode is also an average. And weighted mean is also an average. And these measures of average will depend on the type of data you are working with. Now, apart from summary measures, we also need to know the measures of dispersion. We also need to know the measures of dispersion. Now, if you have a set of data and you're able to conclude that a certain figure is their average by computing the mean, the median, the mode, and the weighted mean, the question you must ask yourself, therefore, is that if, let's say, a figure like 5 is the average of a set of figures. We would also want to be sure that the figure of 5 is a perfect representation of the set of figures, or is a perfect summary of the set of figures. How would we know that? We would know that the average of a set of figures is unbiased, or it is a perfect average of those set of figures when we compute how far each of the individual figures is from their average. So the measures of dispersion, it tells how far the individual figures are from their average, okay? If the individual figures are too far from their average, we can conclude that the measure of average, or the measure of central tendency, or the measure of center and location is not a perfect representation of the set of figures. So always we desire that the measures of dispersion, or the figure we get from calculating the measure of dispersion, should be very small, so that we can then convince ourselves that the individual figures are not too far from their average, okay? Now, before we go into the calculations of measure of average or measure of central tendency, what I want you to know is that we can compute a measure of average or a measure of central tendency for an entire population. And we can compute a measure of average or a measure of central tendency for a sample. Now, any measure that is computed from an entire population, be it mean, mode, standard deviation, or whatever statistical measure that is computed from a population, is called a parameter. So whenever you hear the word parameter, parameter refers to measures that are computed from an entire population. Then, on the other hand, when we compute a measure from a sample that has been selected from the population, that measure is called a statistic. So if I compute standard deviation for a sample of figures, that standard deviation is called a statistic, okay? The generic name for any measure that is computed from a sample that has been selected from a population is called a statistic. So let's start with a parameter called population mean, all right? Now, mean as a measure of central tendency or as a measure of average, it is found by summing all the values and dividing it by the number of items. So we have sigma x over n, okay? So we are going to sum all the values and divide it by the population size, the population size. So if we have a values like 1, 2, 3, 4, and 5, this set of figures, their average is going to be 1 plus 2 plus 3 plus 4 plus 5, okay? And this is 15. And if you want to divide it by the population size or the number of items, they are 1, 2, 3, 4, 5. So divided by 5, so the mean is what? 3. So these kind of computations are quite simple to follow. Now, if you want to compute that parameter, the mean as a parameter, if you want to compute a statistic, it means that we are going to compute the mean for the sample. So the mean for the sample is the set of values in the sample divided by the sample size. So if the population is 1, 2, 3, 4, and 5, the sample will be a set of figures from this population. So I can pick figures such as 3, 4, and 5 to be the sample. So the average of this sample is going to be 3 plus 4 plus 5 divided by 3. So that is 3 plus 4 is 7. plus 5 is 12. So 12 divided by 3 is equal to 4. So this 4 is a sample mean because it is a mean that is calculated from a sample of figures which were obtained from the population. Now, the next measure of central tendency is the median. The median. So median is the center value that divides a data array into two halves. All right. So if you want to compute a median, the first step is that you have to arrange, because median is the center value that divides the data array into two halves. So what it means is that if you want to compute median, you have to arrange the data either by ascending order or by descending order. Then you pick the middle position. How do we know the middle position? The middle position is simply, so the ith, all right, the ith position or the middle position is simply half of the population or the sample size if you are dealing with sample, right? So this will help you know the middle position. Now, let's look at these set of figures. Here we have figures like 1, 2, 3, 4, 5, okay? Figures like 1, 2, 3, 4, 5. How can we find the median? So we have figures like 1, 2, 3, 4, and 5. How can we find the median? The median is finding the ith position, and the ith position is half of the size. So it will be half of, there are 1, 2, 3, 4, 5 figures. So half of 5, the position will be 2.5. Okay, 2.5 position. So we can count it from either backwards or forward. So 1, 2, and half, the figure should be between 2 and 3. Then from backwards, 1, 2, and half, the figure should be between 3 and 4. But you see, anytime the position is not a whole number and it's something like 2.5 position, what we do is that we round it to the nearest whole number. So if you convert this 2.5 position to the nearest whole number, it will be the third position, all right? So the third position is by selecting 3. If you read it from forward, it's 1, 2, 3, which is the third position. If you read it backwards this way, 1, 2, 3 is the third position. So some books argue that whenever the number of figures is an odd number, okay, whenever the number of figures is an odd number, if you want to find the median, the ith or the median position, it will be half into bracket n plus 1. So in this case, it has been half of the number of figures are 1, 2, 3, 4, 5. To 5 plus 1. That will be half of 6. That will be third position, straightforward. Okay, so that's another way of looking at it. Instead of finding 2.5 position and rounding to the third position, whenever the number of figures is an odd number, you can just add 1 to the number of figures. Then you divide it by 2 or half of it, then you get the third position. Now, one thing I want you to know is that, you see, median has a very good quality. Median has a very good quality. One quality of the median that makes it very good is that median is not affected by extreme values. Median is not affected by extreme values. Median is not affected by extreme values. Let me give an example. So for instance, if we have figures like 1, 2, 3, 4, 5, and 1,000, okay? 1, 2, 3, 4, 5, and 1,000. If I want to find the average of these figures, I'll sum the figures and divide by the number of items. So if we sum these figures, I'm sure you are going to get 1,015. and divide it by 6 because there are 6 figures. 1, 2, 3, 4, 5, there are 6 figures. 2015 divided by 6, 2015 divided by 6, that would be 169.12. 17. Now think about it. If these were salaries of people in a company, okay, and we are saying that on the average, these people are taking a salary of 169 cedis, it will not be fair because 5 people in the company, their salary is well below this 169. And one person who collects 1,000 cedis, his salary is well above this 169, okay? So you can see that mean is affected by extreme value, but median is not. Because if I want to find the median of these figures, okay, the figures are 6, all right? The figures are 6. So if I want to find the median, 6 divided by 2 is 3. Okay, the figures are 1, 2, 3, 4, 5, 6. So it will be the third position. So therefore, the third position is 1, 2, 3. That is here, if we read from forward. And if you read from backwards, the third position will be 1, 2, 3. Which is this one, all right? So if you read from forward, the third position is 1, 2, 3. Read from backwards, the third position is 1, 2, 3. So it means that the median should lie between 3 and 4, like this. So when this happens, it will be the figure between 3 and 4. So it will be 3 plus 4 divided by 2, which is 7 divided by 2, which is 3.5. So for this set of figures, when we say their average is 3.5, as in their average as computed by median is 3.5, we can confidently say this is a better representation of an average of these figures than 169.17. So if this is the salary of workers in the company, we can conclude that on the average, the salary is 3.5, which I think is a better average than saying their average salary is 169.17. All right, 169.17. So how do we compute median? The first step is that you collect the data. The second step is that you arrange the data from smallest to largest or from largest to smallest, whichever way. What is important is that the data must be in an array, all right? Now, after doing that, you have to compute the median position. That is half of n. That's the median position. Or if it's an odd number, it will be, if the number of items is an odd number, let's say 5 items or 7 items or whatever, when it happens, the median will be n. The median position of I is equal to half of n plus 1, okay? Then you find the median. So there's an example of a median. These figures have been arranged already in an ascending order. So there are 13 of them. So if you want to find the median, it is half of n plus 1, which is half of 13 figures plus 1, which is half of 14. And the median position will be the 7th position, all right? So you count 1, 2, 3, 4, 5, 6, 7, which is this. Or you can count from backwards, 1, 2, 3, 4, 5. Oh, sorry. So 1, 2, 3, 4, 5, 6, 7. Sorry, it is this, not this. So you can count from backwards, 1, 2, 3, 4, 5, 6, 7. So which is this, all right? Or if you are sticking to half of the nth position, it would have been half of the 13th position, which will be 6.5th position. Then you round it to the nearest whole number, which is the 7th position, and then you choose your answer. So here, the median is the 7th position, and it means that the median is the figure 12. Okay. Now, how do we know whether a figure is affected by extreme value or not? Because we have just learned that whenever a figure is affected by an extreme value, mean is not a best measure of central tendency. Whenever a figure is affected by extreme value, mean is not the best measure of central tendency. The question we ask ourselves, therefore, is that what then is the best measure of central tendency when a figure is affected by extreme value? We've all learned that the best measure of central tendency when the figure is affected by extreme value is the median. But how would we know if a set of figures is indeed affected by extreme value? How we would know is to look at the shape, okay, the shape of the figures. So when we draw the figures using a histogram, all right? So if I draw a figure, or if I draw the set of figures using a histogram, okay? If I represent the set of figures on a histogram, and the histogram looks like this. So I'm just drawing a curve to touch the vertices of the histogram. So if I plot the figures in a histogram and the histogram looks like this, I can confidently say that the figures are evenly spread above their center, okay? Or the figures does not have an extreme value. But when I plot the figures on a histogram and then the shape is looking like this, you can clearly see that the figures are not symmetric, or the figures are not spread about their average, or the figures include an extreme value, all right? So to detect whether a figure is a set of figures, includes an extreme value, we plot them on a histogram and we draw a curve to touch the vertices of the histogram, and we come out with these distributions. So when you draw a set of figures and the shape looks like this, the first one here, okay, it means that the set of figures is right skewed, right skewed. The set of figures is right skewed, okay? The set of figures is right skewed. Please, when we talk about skewness, we look at the tail. So the tail is here. That's why we are saying this set of figures is right skewed. It is not symmetrical, okay? Or the figures are not evenly spread about their mean. So that figure is right skewed. Again, when we plot a set of figures and the tail is here, we say that that figure is left skewed. That figure is left skewed, okay? That figure is left skewed. Now, when we say a figure is left, the set of figures, is left skewed, it means that for those set of figures, definitely their mean will be lesser than their median. When you compute, it will never be the same. And when we say a set of figures is right skewed, for those figures, their median is lesser than their mean. Their median is lesser than their mean. So let's look at this, what I was trying to do earlier. Now look at this set of figures here. All right. For this set of figures, their mean was 169. Their median was 3.5. So it means that their mean is far bigger than their median, or their median is far lesser than their mean. So for this set of figures, if you plot them, it will look like this. It will look like right skewed because the median is far lesser than what? The mean. But you see, if a set of figures is symmetrical or it is evenly spread about their mean, for those set of figures, the mean and the median should give you the same answer. Let me give you an example. Figures like 1, 2, 3, 4, and 5. Their mean will be equal to 15 over 5, which is what? 3. Their median, which is the ith position, will be the third position. Okay, the middle position is the third position, and the answer is also 3. So for this set of figures, when you plot it on a histogram, we can confidently say that this set of figures, it is symmetrical. We can try that. We can try that by plotting them on a histogram. So when you do that, you realize that the middle bar or the median position is 3, which is the same as what? The mean. So this is very important because we need to detect whether the data is affected by extreme value before we can employ the median as a best average. The final measure of central tendency I'm going to talk about is the mode, right? The final measure of central tendency I'm going to talk about is the mode. So mode is the number of figures that occurs most, okay? Mode is the number of figures that occurs most. If I have figures like 1, 2, 2, 3, 4, 5, and 6, the mode is 2 because 2 is appearing most, all right? Now, of course, like the mean, mode is also not, like the median, mode is also not affected by extreme values, okay? That's one advantage of the mode. Another advantage of the mode is that mode can be used for both quantitative and qualitative data. Mode can be used for both quantitative and qualitative data. So this set of figures here is quantitative, all right? Now, if you ask a set of people their color preference, some will choose blue, some will choose red, yellow, another person chooses blue, another person chooses blue, another person chooses yellow, another person chooses violet, another person chooses black. Now we can find the mode of these items, even though they are not figures. So the mode will be the item that appears most, all right? So the item that appears most is the blue color. It has 1, 2, 3. The yellow color just appears 1, 2, all right? So the blue color appears most. So even though these items are not quantities, but they are qualities, mode can be used to compute the average of even qualitative data, all right? Because what is necessary about the data is that you must find the quality that appears most. But the unfortunate thing about mode is that sometimes the set of figures can have more than one mode. For instance, this is blue, this is red, yellow, blue, blue, yellow, violet, and black. If I add another yellow to this set of figures, yellow appears 1, 2, 3 times. And blue also appears 1, 2, 3 times. So in this set of data, the mode is both blue and what? Yellow. Even if I'm using quantitative data, let me add 3 to this set of figures. So in this set of figures, 2 appears twice, 3 also appears twice. That means that the mode again here is 2 and it's also 3. That is the disadvantage of mode, right? So there can be bimodal, okay? Sometimes a set of figures can have no mode. For instance, 1, 2, 3, 4, 5, and 6. These set of figures, it doesn't have any mode. No number appears more than once. Even if you are using qualities like blue, yellow, red, and violet, in this set of qualities or colors, there is also no mode because none of them appears more than once. Okay, so that is also the disadvantage of the mode. Now, what is the best measure? Of course, the best measure of central tendency, first of all, is the mean. Why? Because the mean uses all the figures in calculation. That is why the mean will add all the figures and divide by the number of items. So the best measure of central tendency is the mean. However, if there are extreme values, okay, then mean loses its, pride of being the best because mean is affected by extreme value, okay? So once there are extreme values, mean ceases to be the best measure, because mean is the best measure because mean uses all the figures. It has everything and divide by the number of items. That means that mean is all inclusive. But once it loses its importance, when it has extreme values, then the median will then be used as the best measure of central tendency, because median, as I demonstrated, is not affected by extreme values. Now, finally, we normally employ mode when we are interested in determining the figure that appears most, right? When we are interested in determining the figure that appears most. So let's end with the weighted mean. Okay, let's end with the weighted mean. Now, we can have a set of figures which will have different importance. So for instance, if I have figures like 1, 2, 3, 4, and 5, if I add all these figures and divide by 5, what it means is that I've assumed that each of the figures have equal importance. Okay, each of the figures have equal importance. But if the figure like 1, okay, has more importance like the figure of 5, then the mean cannot be a simple mean. All right, let me give an example. Let's say in a company, somebody has 100 shares, somebody has 500 shares, somebody has 200 shares, somebody has 100 shares, another person who has 100 shares. Okay. Now they are going to vote on the dividend that they should pay. So the person that has 100 shares is saying that, okay, let's pay a dividend of 1 cedi. The person that has 500 shares says that, let's pay a dividend of 2 cedis. The person that has 200 shares says that, let's pay a dividend of 3 cedis. The person who has another 100 shares says, let's pay a dividend of 4 cedis. Another person who has 100 shares also says we should pay a dividend of 5 cedis. Now, what happens? If I want to find the average dividend that the 5 people are saying we should pay, I cannot add 1 plus 2 plus 3 plus 4 plus 5 and divide by 5. It will be wrong, because each of these figures have different importance. If the person who says that we should pay 500, sorry, the person who has 500 shares says we should pay 2 cedis, it will carry more weight than all the other people because he has the highest number of shares. So the weighted mean will be, first of all, we have to compute the weight. So the weight of 1 cedi will be 100 shares divided by the total number of shares. The total number of shares is 100 plus 500, 600 plus 200, 800 plus 100, 100, so 1,000. So the weight of 1 cedi, so the weight of the person who is saying we should pay 1 cedi, his weight is 0.1. The person who is saying we should pay 500 cedis, his weight is 500 divided by the total number of shares, that is 1,000. So you have 0.5. The person who is saying we should pay 3 cedis, he has 200 shares. So his weight will be 200 shares divided by the total number of shares, which is 1,000. You get 0.2. And this person, too, his weight will be 0.1. And the last person, his weight will be 0.1. Okay. So the sum of this weight is what? 1. The sum of the weights is 1. All right. So let's find the weighted mean. Weighted mean is summation of the weight times the figure divided by summation of the weight. So let's multiply the weight by the figures. So we are going to multiply the weight, WIXI, the weight by the figures. So 1 times 0.1 is 0.1. 2 times 0.5 is 1. 3 times 0.2 is 0.6. 4 times 0.1 is 0.4. And then 5 times 0.1 is 0.5. So let's sum them. 0.5 plus 0.4 is 0.9 plus 0.1 is 1 plus 1 is 2, so 2.6. So if you sum everything here, you're going to get 2.6. So summation WIXI over summation WI. The summation of WIXI is 2.6. Okay. Then the summation of the weight is also 1. If you sum all these weights, you're going to get 1. So the weighted mean is 2.6. So normally we use the weighted mean when the figures do not have equal importance, as I've demonstrated here. Okay, so this will bring us to the end of the various measures of central tendencies we have. In the next video, I'm going to teach about the various measures of dispersion. Okay, if you want to compute how far each of the figures is from their average, I'm going to teach that in the next video. So please comment, like, share, and more importantly, subscribe. So see you in the next video. Thank you.